Good morning, students. Myself is Shankar from ECE department, Chevrolet Engineering College. Today, we are going to discuss about the capacitance concepts on capacitance in the same unit, electrostatics. The concepts of capacitance. In the last class, we completed the resistance R is equal to deriving by taking off any conductor with a length of L and applying the voltage V. By deriving this expression, the conventional current and the current is the direction is different. We find the resistance R is equal to. And now we go for the finding of the capacitance or the concept of capacitance. Concept of capacitance. Consider the two conducting materials. You see here in a free space, there is a free space, nothing but is a dielectric. Assume it is a dielectric. In this, the two material we have M1 and M2 materials, M1 and the M2, which is placed in a dielectric medium having permittivity epsilon. The material 1 carrying a positive charge carriers, positive charge Q, while the material M2 carries a negative charge with an equal magnitude as a Q here also. The M2 is carrying the negative charge and M1 is carrying the positive charge, and these two are placed in a dielectric medium. These two are placed in a dielectric medium. We know, and there is no any other charges present, and the total charge on the system is a 0. In conductors, the charge cannot reside within the conductor and resides only on the surface. Okay, remember that the charge cannot reside within the conductor and resides only on the surface. There is a surface having on the surface only there is a charge there, either the positive or the negative. Thus, for M1 and M2, the charge plus Q and the minus Q reside the surfaces M1 and the M2 respectively. Such a system which has two conducting surfaces carrying equal and opposite charges separated by a dielectric is called capacitor system. The two charges are separated and these two are separated with a dielectric epsilon. Is called a capacitor system, which giving rise to a capacitance. Assume these two are the two parallel plates, charge of plus and the minus. In between that, a dielectric constant epsilon, C is equal to epsilon A by D, is a capacitor's beta. The electric field is normal to the conductor surface, and the electric flux is directed from the M1 towards M2, such that see, the electric flux lines from the positive charges is getting generated and terminated at the negative charge carriers. See, for the M1 is a charge is distributed, the positive charges are distributed on the surfaces. M2 is charges, negative charges are distributed on the surface. From the positive charge, there is a magnetic, electric flux lines was terminated and it is generated and it is terminated towards a negative charge. The electric field is normal to the conductor surface and the electric flux is directed from M1 towards M2 in such a system. There exists a potential difference between the two surfaces. There exists a potential difference between the two surfaces of M1 and M2. Let this potential is V12. The ratio of magnitudes of total charge on any one of the two conductors. The ratio of magnitudes of total charge on any one of the two conductors and the potential difference between the conductors is called capacitance. The ratio between of magnitudes of total charge in any one of the two conductors. The charge is a Q. any one of the charge, it's either it's a positive or the negative charge. The charge is Q only. And the potential difference between the two conductors, that is a V12. The ratio between of these two is a C is equal to Q by V12. In general, C is equal to Q by V, where Q is a charge in coulombs and V is a potential difference in the volts. So 1 farad is equal to 1 coulomb per volt. That is a farad. Capacitance in farads, that farad is 1 coulomb per unit. C is equal to Q by V. As the charge Q resides only on the surface of the conductor, it can be obtained from the gas law. We know the gas law is equal to Q is equal to, or psi is equal to, Q is equal to, or psi is equal to integral d bar dot ds bar. D bar dot ds bar. And we know the d bar is epsilon naught or epsilon into E bar dot ds bar. The relation between of D electric flux and the electric field intensity is D bar is equal to epsilon into E bar. Or epsilon means, we know the absolute permittivity epsilon and the relative permittivity epsilon R into E bar dot ds bar. That is nothing but the epsilon only. So ds means it's the surface integral. So the integral surface integral epsilon E bar dot ds bar is a Q. Q is equal to epsilon E bar dot ds bar. Okay. While V is in the work done in moving the unit positive charge from negative charge, moving positive charge from negative charge to the positive surface can be obtained. P is equal to, this is one of the formula. The relation is there for voltage and electric field intensity. V is equal to minus E bar dot dl bar. Line integral E bar dot dl bar. Okay, my dear students. So as the capacitance can be expressed as by using Gauss law, the Q is equal to epsilon E bar dot ds bar, and the voltage in terms of the electric field intensity, that in the line charge E bar dot dl bar. Taking the ratio of these two, the surface integral epsilon E bar dot ds bar whole divided by minus integral E bar dot dl bar. It's a farads coulomb per volt. If the charge is Q is increased, then E bar and D bar get increased by the same factor. The voltage V also increases by the same factor. Thus, the ratio of Q to the V remains constant as a C. As the capacitance is not the function of charge, field intensity, flux intensity, and the potential difference. Okay. Now, the capacitors are in the parallel, the two capacitors of the parallel. You see the capacitor here, the C1 capacitor, C2 capacitor, and C3 capacitor. For all the parallel, we know the C is equal to Q by V, or Q1 is equal to C1 into V, Q2 is equal to C2 into V, and Q3 is equal to C3 into V. The total charge stored in the parallel bank of the capacitor Q is given by the Q is equal to all the charges, whatever we have, the Q1, Q2, and the Q3. So here the one is a positive charge, another one is a negative charge, positive, negative is a capacitor. And combination of the Q1 is a C1V, C2V, C3V, and so on. Taking the V as a common, C1 plus C2 plus C3. So C equivalent will get, applying the voltage V, the charge Q, the totally the C1 plus C2 plus C3 is a C equivalent with the charge of Q and apply the voltage V. Okay. Now it becomes of Q is equal to an equivalent capacitor which stores the same charge at the same voltage V will be Q is equal to C equivalent to V. That C equivalent is a C1, C2, and C3. For n capacitors, the C equivalent is a C1, C2, C1 plus C2 plus C3 and so on into the Cn. Okay. The same formula we have. Parallel plate capacitor. Let us assume here a parallel plate capacitor at the plate 1 with the charge of a positive charge placed at the Z is equal to 0. And another plate, we have the plate 2 with a charge of negative charge, and the charge density is rho s. And here also the charge density is rho s because it is a surface, positive surface, and the negative charge surface. Here the Z is equal to 0, and the plate 2 is placed at the Z is equal to D. A parallel plate capacitor shown in the figure consists of two parallel metallic plates separated by a distance d. The space between the plates is filled with the dielectric. Inside it is a totally the dielectric, either it's 8 or it is whatever. Dielectric filled with the dielectric or permittivity epsilon. The lower plate, plate 1, carries positive charge here, and it is distributed over it with a charge of density rho s. The upper plate, plate 2, carries a negative charge and is distributed over surface with a charge of minus rho s. And it is a plate 1 is placed at the Z is equal to 0 in XY plane. As it is a normal to the direction of the Z. You see the plate here, and it is a normal to the direction of the Z. Means the differential surface area normal to the Z direction. That differential surface area is in the XY plane only. Okay. XY plane has a normal to its Z direction. While upper plate is 2 is in the Z is equal to D, because it is a distance from the plate 1 to the plate 2 is a D, means it is the plate 2 is at the Z is equal to D. It's a parallel to the XY plane. Exactly, it is a parallel to the XY plane. You can keep another plate here, the distance of the D. It is a negative charge with the density of rho s, and here with the density of rho s is a positive. That A is the area of cross section of the plates in the meter square, and we know the formula is there. That formula is that Q is equal to C. Q is equal to C is equal to Q by B actually. Q by B, that B is equal to, here it is represented as a rho s into A. The charge density into area. The charge density rho s into the area. The surface you can consider here, that V is a rho s into A of C. And now, the magnitude of a charge on any one of the plate as both is equal in magnitude. To find the potential difference, let us obtain the E bar between the plates. Assume the plate 1 is an infinite sheet of charge. Assume the plate 1 to be the infinite sheet of charge. So E1 is equal to the infinite charge. The E1 is raised by the 2 epsilon only. It's a formula for the E bar due to the infinite sheet of charge. E bar due to the infinite sheet of charge. Rho is by the 2 epsilon, where rho is this charge density, and the direction is AN bar. Now it is take as AX bar here. The E1 bar is a normal at the boundary between the conductor and the dielectric without any tangential component. So the E1 is at the positive charge density, and E2 is for the negative charge density, rho s minus rho s by the 2 epsilon, and it is a AN bar, and E1 is towards the direction is a positive direction, and it is a N bar for the plate 2 is a minus the negative direction, the positive direction and the negative direction. Both direction is a positive. So the E1 is in the positive charge. The direction of Z is a positive here. So plate 1. Plate 1 is on the XY plane, and the plate 2 is also parallel to the XY plane, but with a distance of t, with a negative charge density is there, and the direction is towards the downwards. The positive charge is a AZ bar, and for the negative charge uniformly distributed on the plate 2 is the direction is minus AZ bar. Minus AZ bar. So the E1 is equal to rho S by epsilon. The AN is a AZ bar, that is a positive here, volts per meter. And E2 we can see here, minus rho S, the charge density is a minus rho S by 2 epsilon. The AN is equal to, the AN is a negative direction here, that minus AZ bar. So totally it is also becomes of rho S by 3 epsilon into AZ bar, volts per minute, volts per meter. Okay, the total electric field E bar is equal to E1 bar plus E2 bar is a rho S by 2 epsilon AZ bar, rho S by 2 epsilon into AZ bar. So take the AZ bar and the 2 rho S by the 2 epsilon, the 2 to get cancelled, rho S by epsilon into AZ bar is the total E1 bar plus E2 bar. Okay. The potential difference, the V is equal to, you know the formula, the V is equal to minus integral E bar dot DL bar is equal to the upper limit and the lower limit here. The upper is a negative values and the lower is a positive. Why I am saying it is upper is a negative here, the upper plate, the plate 2 is a negative, and the lower plate is there at Z is equal to 0, that is a positive value here. So rho S by epsilon is an E value, rho S by epsilon into AZ bar dot DL bar. What is the DL bar here? Dx into AX bar plus dy into AY bar plus dz into AZ bar in the Cartesian coordinate system. You know, in the Cartesian coordinate system, the differential length DL bar is equal to having the 3 components are there, differential components, dx, dy, and the dz, you know. And the dx is in the x direction, dy is in the y direction, and the dz is in the AZ direction. What it matters to us. Now, substitute the DL bar here. In the voltage V is equal to, we got the minus integral upper, actually it is upper limit and the lower limit we are saying. Why I am taking here it is upper means the negative sign is for the upper plate and positive charge for the lower plate. So rho S by epsilon into AZ bar dot DL bar is equal to dx AX, dy AY, and the dz AZ into combination. So after substituting the value of DL bar here, the rho S by epsilon into AZ bar only, AZ bar dot AX bar is 0, AZ bar dot AY bar is also 0, and AZ and the AZ bar only the value is a 1 because the dot product itself is a 1. So AZ bar dot AZ bar is equal to 1. Okay. So what is the magnitude of AZ bar here? The rho S by epsilon. And what is the magnitude of AZ bar here? It is a dz. So rho S by epsilon into dz. And what is the upper value and the lower value? Upper value that is the d, lower at the z is equal to 0. So z is equal to d to the 0, rho S by epsilon into dz. So with respect to applying the z values, so limitations is also at the z bound. So negative charge is at the distance d and the positive charge at the z is equal to 0. So rho S by epsilon is a constant, integral dz is a z, upper limit is a 0 and lower limit is a d. So rho S 0 minus d by epsilon. So you'll get the minus into minus again, it's a plus. V is equal to rho S d epsilon volts. Okay. V is equal to rho S d by epsilon. The units is a volts. We know the formula of the capacitance, so C is equal to Q by V, where the Q is equal to rho S into A by rho S d by epsilon. Why I wrote this rho S by A, you can See, my dear students, here Q is equal to, or we know, change of the charge with respect to the volume is equal to rho V. Or change of the charge with respect to the S, ds is equal to rho S. Change of the charge with respect to the length, dl is equal to rho L. Length means having only the 2 points is joined, is a length, you get. And by adding these to the total, it is becomes of a surface. The surface means L into side is a area. Okay, it is also L, length and the breadth, let us take here. Area is equal to L into B. Alright. So the differential surface or the ds, dq by ds is equal to rho S, or dq is equal to rho S into ds. So if I am taking only the q is equal to rho S into S. What is that S? Nothing but is the area L into B. So S I am representing as the area A into, so Q is equal to rho S into A. Q is equal to rho S into A because it's a surface. The charge is distributed on the surface, that is equal to 0. That is a plate 1. And charge is distributed, the negative charge is distributed on the plate 2. That is also placed at the Z is equal to D and Z is equal to 0 here. So that is total having the surface is the area. Q is equal to rho S A by the V, rho S D by epsilon. So rho S get cancelled, epsilon A by D. Okay, epsilon is here, we'll get in the numerator epsilon A by D. So the capacitance C is equal to epsilon A by D is a farads, where epsilon is a epsilon naught and epsilon R A by the D. So it can be seen that the value of capacitance depends on the permittivity of dielectric used, the area of cross section of the plates, distance of separation of the plates. It is not depends on the charge. So it is not depends on the charge, or it is not depends on the potential difference between the plates. The capacitance is not depends upon the charge and not depends upon the potential difference between the plates. It is on the permittivity of the dielectric, or the area of cross section, or the distance separation of the plates. Means C is proportional to the area and inversely proportional to the distance. C is equal to epsilon A by D. So same thing, the capacitance, have to find out the capacitance of the coaxial cable. See the coaxial cable look like here. Outer ring here, outer circle is the radius of B, inner circle with the radius of A. In between of these two, these two circles, there is a dielectric is there. Assume that it is a dielectric is there inside. With the radius of A is charged with the positive values, positive charges, and with the radius of B, charge the outer radius, charge with the negative. Consider a coaxial cable or coaxial capacitor that A is the inner radius and the B is outer radius. The two concentric conductors are separated by a dielectric. Means inside, in between, there is a dielectric. The length of the cable is a L. The total length of the cable from here itself. Length of the cable is L. The inner conductor carries a charge of density rho L plus on the surface. Then the equal opposite charge density rho L Coulomb per meter square exists on the outer conductor. Is a negative charge, it is outer conductor is a negative and inner conductor is a positive. So Q is equal to rho L into L. Now only I explained that dQ by dL is equal to rho L. Charge density or length of the charge density and the change of charge with respect to the length, or Q is equal to rho L into L. The same thing, the Q is equal to rho L into L. Assume that cylindrical coordinate system, E bar will be radial from inner to the outer conductor, and for the infinite line charge, E bar due to the infinite line charge, E bar is equal to rho L by the 2 pi epsilon naught R into R bar. These are formulae we already derived. Infinite charge. For the point charge, the E bar is equal to, for the point charge, E bar is equal to Q by 4 pi epsilon naught R square into AR bar. This is a formula for the point charge. This is electric field intensity for infinite line charge, rho L by the 2 pi epsilon into R AR bar. And E bar, due to the infinite sheet of charge, now we see that is rho S by epsilon naught into AR bar. Rho S by epsilon naught, rho S by the 2 into epsilon, not the epsilon naught, 2 into epsilon. When it is a free space, it is becomes epsilon is epsilon naught. These are the formulas we have for the electric field intensity. It's a point charge, infinite line charge, and infinite sheet of charge. So I use here infinite line charge E bar is equal to rho L by the 2 pi epsilon R into AR bar. Rho L by the 2 pi epsilon naught R into AR bar. Okay. Now the potential difference, E bar is directed from inner conductor to the outer conductor. The potential difference is work done in moving the unit charge against E bar from R is equal to P to the R is equal to E. The potential difference, the dl bar, the V is equal to minus integral E bar dot dl bar. See, the negative charge is for the radius of B and positive charge is for the radius of A. The inner radius and outer radius is charged with the negative. So R is equal to B and R is equal to A, and E bar is infinite line charge rho L by 2 pi epsilon naught AR bar dot. And here the dl bar is equal to differential length. Consider the differential length radial direction, which is dr into AR bar. dr into AR bar. The same thing, what I assume the dl bar, a small differential length, any on the surface here, positive to the negative here. Means the differential length is towards the direction of R only. Okay, towards the direction of R, that is dl is equal to dr into AR bar. Why I am taking this only one term? Directly you can substitute the dl bar is equal to dr into AR bar. Nothing will happen, my dear students. So plus another one is there, R into d phi, A phi bar, plus, and another one is there, dz into AZ bar. Is AZ. So here we have only the AR. So I am using the dl bar is equal to dr into AR bar only. I am not taking the A phi and AZ, becomes a 0. The dot product itself is a 1, AR bar dot AR bar. So the coefficients are rho L by the 2 pi epsilon and dr is there, dr, and AR bar dot AR bar is equal to 1. So integral dr, and R is there, integral of rho L by the 2 pi epsilon. See, my dear students, here the R is there, 1 by R into dr. AR bar dot AR bar is a 1. 1 by R into dr is a ln of R. The integral of 1 by R is equal. So upper limit is A and lower limit is B. So minus, already the minus is the voltage function, minus E bar dot dl bar. After substituting the E bar as a infinite line charge, the dl bar having the R component only, rho L by 2 pi epsilon into ln of A by B, because it's a minus is there, we represent it as A by B. And change is negative also by changing of B by A, rho L by 2 pi epsilon ln of B by A. Whenever you are interchanging the negative here, it's a positive difference. So voltage we got. Now we can find the capacitance C is equal to Q by B. And this Q, previously we wrote that is a rho S into A. but now it is a length. We are taking the coaxial cables, or it's a length. So length is a Q is equal to rho L into L. Rho L into L, and the V we got is the rho L by the 2 pi epsilon ln of B by A. So rho L get cancelled. 2 pi epsilon will in the numerator, 2 pi epsilon into L, ln of B by A. The capacitance is a farads. Capacitance of coaxial cable. Capacitance of a parallel plate capacitor is epsilon naught and epsilon R A by D, where C is equal to, and the C is equal to the Q by A. The capacitance is not changes with the charge and not changes with the voltage, and it is a change of the area is increases, the capacitance increases, D increases, the capacitance is decreases. Now the coaxial cable C is equal to, we got 2 pi epsilon A L by the length of the coaxial cable, ln of outer radius of B and the inner radius PA. This is a farads. Okay. The next topic is a spherical capacitor. Spherical capacitor. Parallel plate capacitor we seen, and the coaxial cable or coaxial capacitor. Now it is a spherical capacitor. So assume here the diagram shows it's a spherical capacitor. Consider a spherical capacitor. Consider a spherical capacitor formed of two concentric spherical conducting shells of radius A. The inner radius is A and outer radius is a B. Concentric spherical conducting shells. The radius of outer surface is a P, while the inner surface is a A. Thus, the P is always greater than A. The region between of the two spheres is filled with the dielectric of permittivity epsilon. The inner sphere is given as a positive charge, and while outer surface is the charge Q. The same concept what we are taking there. It is a parallel plate capacitor. There is a parallel plates of only the surfaces. And coming to the coaxial cables with having the length, the inner radius of A and the outer radius of B. Outer radius is charged with the negative, and inner radius is charged with the inner cable is charged with the positive. And now I am assuming here a spherical shell, connecting shells with the radius of A inside with a positive charge, and conducting shell of radius B with a charge minus Q. And considering the Gaussian surface as a sphere of radius R, in between of A and B, or inside of A and outside of the B and A. See, there is a three cases when I am assuming the Gaussian surface of inside here, inside, and I assume the Gaussian surface of in between of a radius of A and B, and assume the Gaussian surface outside the circle, Gaussian surface with the sphere of radius R. It can be obtained that E bar is given in the radial direction and is given by a point charge. We know the electric field intensity Q by 4 pi epsilon naught R square into AR bar. Q by 4 pi epsilon naught R square into AR bar, volts per meter. And the potential difference is a work done in moving the unit positive charge against the direction of E bar, and R is equal to B and R is equal to A. B is equal to minus integral the negative charge for the radius of B, outermost, and the positive charge is for the inner radius spherical shell, or E bar is equal to Q by 4 pi epsilon naught R square into R bar dot DL bar. Is a shell, so DL bar is equal to DR into AR. The remaining is here the spherical shell means a spherical coordinate system I described. So spherical coordinate system DR, d theta and the d phi. Even it is E is equal to AR bar means I am taking only the AR bar only. The remaining two terms I am not mentioning here. So minus R is equal to B, R is equal to A, Q by 4 pi epsilon naught R square, AR bar dot DR into AR. So AR bar dot AR bar is equal to 1, and Q is a constant, 4 pi epsilon is also constant, and we have 1 by R square into DR. 1 by the integral 1 by R square into DR. What is the integral of this one? It's the integral of R power minus 2 dr. That is the integral of anything power. The value as a 1 by R square is equal to 1 by R square. Here the 1 by R square is there. R power minus 1. 1 by R power n. R power n plus 1 by n plus 1. The integral value. So R power minus 2 plus 1 by the integral minus 2 plus 1. So minus 2 plus 1 is a minus, and R power minus 2 plus 1 is a 1 by R. 1 by R. So 1 by R with the upper limit is A and lower limit is a B. So 1 by A minus 1 by B. So when I am substituting the upper limit, it becomes of 1 by A minus 1 by B. Already the function is a minus already here the voltage is also B. So minus into minus becomes a plus. So V is equal to Q by 4 pi epsilon naught 1 by A minus 1 by B volts. Now this voltage V and the charge Q is substituting the C is equal to Q by V. Here it is not the length and it is not the surface there. It is only the charge with a circular shell, spherical shell it is, having the negative charge as outermost and the positive charge as the innermost. So for that I am taking the point charges on. Point charge of electric field intensity bar is equal to. So Q by 4 pi epsilon naught into 1 by A minus 1 by B. Q get cancelled. C is equal to 4 pi epsilon naught by 1 minus A minus 1 by B. 1 by A minus 1 by B. What it matters to us. So now, on the concept of capacitance, we learn that it's three different types. One is a parallel plate capacitor, another one is a spherical shell and a coaxial capacitor. What it matters to us. In this, today we learn that spherical capacitor, another one is the capacitance of a coaxial cable, and parallel plate capacitor, 3 terms is a capacitance. Okay, my dear friends.